HPNI, Professor A.K. Tyagi, Registrar HPNI, Professor P.C. Selvin, Associate and Assistant Deans of HPNI, senior faculty members, HPNI staff members, students, and all those who have joined us online. A very good afternoon to all of you. We have all assembled here to attend the third Srikumar Banerjee Memorial Lecture organized by HPNI. Our esteemed chief guest, Dr. Dipendra Singh, Chairman and Managing Director, Indian Railway Limited, has generously accepted our invitation and agreed to deliver a talk titled Railroads, Discovery, Development, and Deliverables. Thank you, sir. A few lines about Dr. Banerjee as we have here. Dr. Srikumar Banerjee was a great academician and leader, as well as an accomplished engineer and scientist with innovative thoughts and ideas. He held many important positions such as Director, Bhabha Atomic Research Center, Chairman, Atomic Energy Commission, Secretary, Department of Atomic Energy, and he also served as Chancellor of HPNI. Yet, he was nothing but excellence and simplicity personified. Though he is not with us in form today, his scientific spirit shall be our guiding beacon forever. With these few lines, I would now request Dean HPNI, Professor A.K. Tyagi, to deliver the welcome address.
Dr. Dipendra Singh, CMD IREL, and chief guest of today's program. Professor Kamachi Murli, Honorable Vice Chancellor, HPNI, respected Shri A.K. Anand Sir, colleagues from HPNI Central Office, Ashri Dr. Tiwari, Dr. Arya, many other senior colleagues, invitees and students present in person and online. I welcome you all to this Dr. Srikumar Banerjee Memorial Lecture for the year 2024. As Dr. Rachna mentioned, Dr. Srikumar Banerjee was a unique combination of a great scientist, remarkable administrator, wonderful human being, and a great visionary. Most of us had opportunity to interact with him and got tremendously benefited by our association with him. He was born on April 25th, 1946, obtained his BTech in metallurgy from IIT Kharagpur, and then joined 11th batch of BRC Training School. May 23rd, 2021 was an extremely sad day for all of us. In fact, just a day before, I had a long discussion with him on phone. And that particular day, Sunday, we were supposed to talk for a longer time in the context of his talk on the occasion of TIFR Foundation Day on June 1st. But that never happened. In the morning, we got the news, very sad news, that we have lost him untimely. He has left behind a rich legacy of wide spectrum of science and technology. He had a wide range of interests in the field of shear memory alloys, phase transitions, electron microscopy, crystallography, quasi-crystals, just to name a few. He was a strong supporter of self-reliance, Atmanirbharta, in the field of rare earths. He had a strong association with HBNI in many ways, such as Member Academic Council, Chairman Com. As already mentioned, he was also Chancellor of HBNI. In order to pay rich tributes to this great visionary whom we lost untimely, HBNI initiated Dr. Srikumar Banerjee Memorial Lecture. As I mentioned, that he had a strong interest in rare earths program in DAE. This year we thought, who can be a better speaker than Dr. Singh to speak on this occasion and pay tribute to him. I would like to once again thank you for kindly sparing your valuable time to be with us, to enlighten us on latest developments on this important area of national importance. Let me once again welcome you all for today's program. Thank you very much.
Thank you so much, sir, for a warm welcome. May I now request Honorable Vice Chancellor HBNI to present a bouquet of flowers to our Chief Guest, Dr. Dipendra Singh, as a token of our respect and admiration. We will have to. Thank you, Professor Mudali and Dr. Singh. Now I request Honorable Vice Chancellor Professor Mudali to kindly deliver presidential address and introduce the speaker for the day.
The chief guest for the today's Dr. Srikumar Banerjee Memorial Program, Mr. Dipendra Singh, Mr. Anand, Professor Tyagi, Professor Selvin, my senior colleagues at HPNI, senior colleagues from BRC and other CIs and OCC who are attending both online and physically present here. A warm welcome to all of you for the third Dr. Srikumar Banerjee Memorial Program, which is being conducted today. Due to the availability of the speaker, the date was chosen today. Otherwise, this should have been done on 24th of 21st of May. So no, 23rd is holiday. So we thought we'll do it on 24th, but due to availability of Mr. D. Singh, so we have fixed it on this date. And there were two reasons. One is that Mr. Singh had very close association with Dr. Banerjee. I am personally aware of that. And second thing is that the topic, rare earth minerals and materials, is very close to the heart of Dr. Banerjee. He has been very passionate about it. And we have heard him many times, in proposing that there should be wider R&D and technology development in our country for self-reliance in rare earth materials towards various applications in the advancement. I'm very proud that Mr. D. Singh has accepted our invitation. Mr. D. Singh has varied experience spanning over 35 years in the field of strategic corporate planning, project management, production planning and control and quality management, human resources management, skill development and industrial training. And before being appointed as the CMD of IREL, he was also Director Marketing at IREL and Director Corporate Planning and Business Development at EDSIL India Limited. He is an MTech, he is an engineer with MTech specialization in industrial design and also MBA in marketing. All of us must be wondering that he is not a metallurgist and who will not speak about microscopy. So this is another reason that Dr. Banerjee is very passionate about a wide range of topics. But we always try to identify only with microscopy. The first two speakers were microscopists, Professor Indranil Manna and Dr. G.K. Day, very close associates working on the microscopy. So we thought that we should call another person who is very close to Dr. Banerjee and also working on a topic which is very passionate to Dr. Banerjee's interests. And Mr. Singh has been associated with IREL and also with this topic of rare earth materials and minerals, I think for nearly 2 decades. And he has made excellent contribution to the growth of rare earth materials in our country. He has been duly recognized by various prestigious awards, including the Lifetime Achievement Award for excellent contribution in the field of rare earth in India by the Rare Earth Association of India, and Eminent Engineering Personality by the Institution of Engineers, Outstanding Business Leadership Award from the Institute of Economic Studies, Best CEO Corporate Management Innovative Excellence Award, CSIR CLRI Padma Bhushan Dr. Nayudamma Kemkan Distinguished Speaker Award, CEO of the Year Award by National Feather Award, National Feather, Leading Director Award, CEO with HR Orientation Award. I think I can keep add the recognition that he has received by his outstanding contribution in corporate management. And professionally also he has been very active. He is the chairman of the Indian Institute of Metals Mumbai chapter, through which he was very close to Dr. Banerjee in organizing various events, including the successful National Metallurgist Indian Institute of Metals annual meeting at Mumbai. And he is also president of the Rare Earth Association of India and chairman of Western Region CAPEXIL and research council member of CSIR NIIST Trivandrum and CSIR IMMT Bhubaneswar, and governing board member of Skill Council of Mining Sector and many other professional affiliations. We are very proud and delighted that he accepted our invitation. In fact, he was very much emotional when we talk about Dr. Banerjee and that he should deliver the memorial program. He was very excited. He felt that this is one contribution that I can make for my interaction with Dr. Banerjee, and his support during his tenure as the chairman, giving all the support to IREL and the rare earth materials activities. I think without taking much time, it is my pleasant duty now to invite Mr. Deependra Singh, CMD IREL, to deliver the talk on rare earths discovery, development and deliverables. And maybe that we'll pay homage and then start the lecture. Upload the people.
Good afternoon, Honorable VC of HBNI, Professor Kamakshi Mudali, respected Grover Sahib, respected Professor Anand, Professor Tyagi, my colleagues from BARC and other scientific fraternity across the country, from DAE family, and dear students. So it is a proud privilege for me to be amongst all of you to speak on this occasion of memorial program of Dr. Srikumar Banerjee. And I would like to recall that when I joined DAE family, Dr. Banerjee was the chairman AEC and also he was the secretary DAE. So during his tenure as secretary, I joined this family. And then at that time, rare earths there was no plant. Of course, there was one plant of IREL, but that was stopped in 2004. So this rejuvenation of the rare earths took place at that time. And then that plant started production by 2016-17. And today we have the self-reliance in this field. In addition, he has also introduced me to IIM and I joined IIM and then today I'm the chairman of the Mumbai chapter. So I have enjoyed a very close relationship with him and his mentorship for learning various aspects of this field and also networking in the field. Second important aspect is that actually I could see a lot of my colleagues who are working with me on this rare earths from BARC, and together we could do something which is a step forward in the value chain of rare earths, and we all cherish that together. But this particular presentation basically is meant for the students. So I would go a little primitive in this, but I hope that this will be definitely informative for them. So starting with So these are the contents which I'll be presenting. So I'm starting with the critical materials because this is a buzzword today in the country, and everywhere this critical material is talked about. And I'm also fascinated with that because earlier in this kind of series of material, only rare earths was produced in the country. And we were finding that there were hardly very few takers about our logic, our ideas. But since the day the critical material has become a need of the country, then I have found that we are better understood at various platforms. So this is the reason I thought I would first explain about the critical material. So these are the substance which are crucial to technology with limited alternative and supply risk. So basically, critical materials are not means considered which are in the upstream side. Rather, it is considered towards the downstream side, because if we are manufacturing certain items or certain product, and among various input, if some of the input we find there is a supply risk or there is no substitute available or alternatives are not there, then that enters in the list of critical material. So by virtue of its definition, the mostly such list will be released by the developed country. And we will not find the list of critical material with the countries who are developing or underdeveloped. So once that need is felt in the country, it means we are progressing towards that direction. And this critical material depends on who is using it or who is going to identify it, because it may vary from person to person, country to country. So in simple word, we can say that it is something which we really need it, but may not get always the way we want. The way we want will include in the form, at the cost, at the price, at the time when we are needing it. So how material criticality is affected today? Some of the examples, like if I'm taking a very simple example of loudspeaker, which uses the magnet of or high performance magnet, and nowadays this rare earth permanent magnet is used. So if these prices are increased, then it would affect severely the loudspeaker manufacturers. So similar is the case of with electric vehicles. This Tesla Motors or any electric vehicle producer might cut production if the battery shortage is there or RE permanent magnet shortage is there. And many a time, a military hardware which are based on these critical material, including the rare earths, and they are mostly sourced today from China. So due to lack of domestic supply, so when this production is affected, then also the criticality of material is experienced. Similarly, it is related within the LED and phosphors, where for the sake of achieving energy efficiency, we may feel shortage of the material. So there is the 3D approach, and this 3D approach is matching to my title of today. That is, again, my title of my program is also related with 3D. So what is the 3D approach with respect to critical material or rare earths? That is to diverse the supply. Normally, it is not very easy, because when we study the list of critical materials, mostly it is concentrated. Same is the case of rare earths. The second approach is to develop the substitute. Again, that would not be very easy. And third approach is to drive reuse or recycling, which is also called the urban mining. And with this 3D approach, the criticality of the material can be reduced. So this is an important aspect which I'm going to talk now. Mine development is of a known resource. Suppose the resource is known. The international standard says that it takes about 15 years to develop a mine, to bring it to a stage when the output of the mine can be effectively used by the industry, and at the same time it would cost billions of dollars. But Development and deployment of such material takes average of 18 years. So this indicates that if we need some material, the planning has to be well in advance, at least 2 decades in advance. One need to plan for the material, and therefore there is a lot of importance to the material science as a subject and the scientists who are involved in it, because they have to not only envisage what would be needing 2 decades later, at the same time they have to develop the methods, tools, techniques, and methodology to reach to that level. So therefore the planning aspect is very much inbuilt with this subject, and we have to take into cognizance that. At the same time, as far as recycling program is concerned, there is no empirical formula. Well, we cannot go through the mathematical modeling to this. So all recycling will be depending on the individual material, and therefore it has to be done when it is available with us, or the technology will develop when it is available with us. So how the new critical materials are getting developed, like rare earth itself. When I look back, say 2-3 years back, where we have had our platinum jubilee. So I have studied all the documents which are available with IRL since 1950 and 1952. So we have found that though we started production of rare earths in 1952, but till 1970 there was hardly any taker, and we were just providing the supply of strategic material to BARC, and rest of the material was stockpiled. And only thereafter the user community has developed, but not in India, that has developed globally. And then some of our material start moving. So this is a specific aspect of such material. Their emergence will happen at a particular point of time. And how it happens, that it starts with supply shortfall. With that, the demand spike will take place. And it is very difficult to predict that to what level this demand spike will take place, or to what level the supply shortfall will take place. So it is normal that we may not be in position to predict that, and then responding that would become difficult. So therefore, this also leads to a proper planning well in advance, so that we are in position to respond it when the need arises. So working on the problems of today to prepare for the problems of tomorrow. So what we need: better foresight through improved economic analysis, expeditious response through improved technical capabilities, learning from industry, because many a time what we see in the academics or what we see in the laboratory, in industry, we find the things are responding in entirely different manner, or sometimes the development may take place in a different manner. And also learning from the history is very important in this aspect. So in case of challenges, with respect to the rare earths, we find that there are 3 major challenges. First is separation. So this we have achieved in India. Second is smelting. We are in the process with the help of BARC. And this is the area where this Bhopal plant is set up. And third is understanding the F electron. So this F electron issue with rare earths would be instrumental in processing various individual rare earths, because the same molten salt analysis process would behave differently with different elements. So role of critical minerals in clean energy transition. So energy security challenges in clean energy transition. So first and foremost is rare earths, which are considered essential for permanent magnets, and in terms of wind turbine and EV motors, both are meant for clean energy purpose. And with the clean energy drive, we see that there is a requirement of huge increase of these materials, and therefore the energy sector is emerging as a major force. And most of the countries, the Department of Energy handles all these material. By 2040, the clean technology are expected to grow over 40%, and such material like copper, rare earth element, demand would increase by 40%. and 60 to 70% demand would increase for nickel and cobalt, and almost 90% demand would increase for the lithium. This is what the estimate by Department of Energy of US. So when all the countries will accelerate their program for emission reduction, then this will ensure resilient and secured energy systems, and such system will become even more important. Now, one such example, if we look at with terms of the clean energy technologies, so transporting in terms of kg per vehicle from the conventional car to electric car, all these the materials usage is going to increase multifold. As it is seen here, it will be around 3 times roughly the material requirement will increase. The maximum increase we'll find in terms of copper, lithium, and rare earths. Then for power generation, when we look at kg per megawatt, again with respect to these materials, the offshore wind energy, there would be maximum requirement of this material. This offshore wind energy sector is yet to come in a big way in the country. So this is a open avenue for development for our country. Onshore also, these materials are used in a big quantity. Then comes the solar PV, nuclear, and natural gas, as well as the coal. So in all the cases, wherever the energy security is important or the material related with energy securities are there, for the sake of clean energy, this material consumption is likely to increase multifold. Now here we can see the share of clean energy technologies for the select materials. So by 2020 to 2040, the lithium is the material which is going to increase the maximum, the first bar diagram. And then rare earth element also, we can see that in comparison to 2010, there is almost more than 3 times increase in the consumption of rare earths. And similar is the thing with the cobalt, nickel, and copper, etc. Now, future impact of clean energy transition for metal and mining. So demand trajectories for the critical minerals are subject to the uncertainties driven by technology as well as the policy factors, because policy is again very important. That maybe the electric vehicles are important for the country, but depending on the resources, to what extent the policy makers are going to adopt it, or to what extent the resources can be created, that would play a major role. So again, depending on the choice of wind turbine, the strength of policy support, then a rare earth element may see 3 to 7 times a higher demand or increase by 2040. And looking at that, we at IREL, we have initiated the activity or action to improve our capacities and capabilities by first by 2030, 2032, and then second phase 2040. So now what are the discouraging factor in this side? See, revenue from coal production is 10 times larger today than this energy transition material. So in general, the attraction of the industry is less. But by 2040, it is expected that revenue from these materials may overtake the revenue from the coal. So this way it can be said that it is the material for the future. So now mineral demand for clean energy technologies by the scenario. So these sectors by 2020 to for achieving the net zero by 2050. So what would be the share of wind energy, solar, PV, then electricity networks, which includes the nuclear energy, and EVs and battery storage? It is shown here. And we can see that the EVs and battery storage segment is showing the maximum increase for achieving the net zero. And therefore, the requirement of these materials, including rare earths, would be increasing multifold. So growth of some of the selected material for sustainable energy requirement. So here also rare earth is finding its place, and the increase is of course low comparison to lithium, but even then this is phenomenal because of the complexity associated with the material separation and the extraction. Then coal versus energy transition material. So here a comparison is shown 2020 versus 2040. So the share of energy transition minerals is very low vis-a-vis coal in 2020, and it is showing increase by 2030, but by 2040, a combination of various material and its share is overtaking the share of the coal. So that way it is expected to increase the revenues also with respect to coal. And then more and more industries are expected to be attracted toward this sector. So what are the vulnerability that may increase the market tightness and price volatility, which is the major concern with such material? So that is high geographical concentration of production. Normally, it is the advanced countries where such production takes place. Long project development lead time. This is a big issue, and we come across very often while working with rare earths. Then declining resource quality. This we have seen in our own mines. What was the content from the mine by 1970? Today, the content has reduced considerably. And besides the reduction of content, the grain size also reduces. So thereby it affects the recovery factor, and therefore the more efforts are required to be done here. Then growing scrutiny of environment and social performance. We know that all these statutory requirements have been introduced post 1986 in the country. So whereas when IRL started this work, at the time none of them was there. So transition from that era to the new era and preparing the manpower for that purpose, this itself is a Herculean task. And higher exposure to the climate risk, that is a well-known fact. Now, this is a good comparison which shows that many times, especially in the case of rare earths, I have seen that in various forums also, we have been made to answer it. The questions like that, why we cannot mine like China, or why we cannot produce like China rare earths. So answer is inbuilt here. Basically, the resources, as far as resources are concerned or mining is concerned, about all these essential minerals, here the 5 minerals are compared: copper, nickel, cobalt, rare earths, and lithium. So out of these 5 minerals, if you look at cobalt, so cobalt is not available in China, but still they are producing roughly 60% of the world cobalt. So from where they are producing? Then same way, China is having around 60% of, actually 44% of the reserves, global reserves, but they are producing rare earths about 80% of the global reserve. So basically, it does not depend whether on mine is there or reserves are there, any kind of production. It is depending on the technology to process, technology to refine. So in case of rare earths, we know very well, China is mining everywhere in the world. They have been importing ore from US, Brazil, Burundi in Africa, then also Australia, and then they were all processing in China, and therefore they are the biggest producer of rare earths. It is not everything mined there, rather taken from the various sources globally. Similarly, cobalt, there is hardly any production, mines or reserves in China, but they produce 60% cobalt. Same is the case with lithium. Their reserves are 12% of the world, but they produce 85, around more than 75% of the lithium metal. So what matters is processing and technology to refine. Availability of mine and availability of reserves is secondary to that. This is about the rare earths, which everyone is knowing well, so I'll not give much stress to this. Now, this is another important aspect which I would like to share here. This is the discovery timeline of rare earth element globally. So out of this 17 element, if we look at, we will find that all these 17 elements were discovered before 1910, is before First World War. The last one, promethium, is been discovered in 1945. So when all these elements have been discovered so early, then why they have not been used for a long time? Their usage came into the picture only after 1970 to some extent, and post 2000 to a bigger extent.
इसका फ्यूजर ये फ्यूजर का इशू है फ्यूजर कुछ 5000 या 6000 कुछ रहता है बाहर
The reason is very
तो
simple.
इसलिए बाहर से करना बाहर से करवा दो कुछ
पता करो रेट पता
The reason is very simple, that the rare earths are the element which cannot make any product in itself. They can't be value added within themselves. Rather, they are used to value add the other functional material. So they are mostly playing the catalytic role. Initially, I was hearing that efforts to be made for value addition of rare earths, but that is absolutely a wrong phenomenon. Value addition of rare earths cannot be done. Rare earths are used for value addition of the other element. For example, NdFeB permanent magnet, when we say that, basically Fe is the magnetic material, and when we add Nd rare earths into that, it increases the magnetic property of iron multifold. Similar is the case of various other element. If you look at the fluid tracking catalyst, there also the addition of rare earth based catalyst improves the performance of catalyst for refining of the crude petroleum. So that is the reason that though they have been discovered much earlier prior to First World War, but their usage started much later when there was need of advanced technology, when there was need of efficiency, when there was need of something beyond, means with the efforts of the human being which has to be obtained. So these are some of the reserves, but these reserves, of course, Indian reserves are also in the public domain, but I would like to share my personal experience which we have got while moving across globally. How relevant are these data? In Vietnam, on the direction of Government of India, last year we have visited to do a means field study, what kind of results and whether we, with our technology, we can process it, refine it. So after having an extensive visit to their mining areas, when we sat with their ministry and we started talking about their reserves, and we said that you have 22% of reserves of the global reserves. So they said that we are not sure that we have 22%. So then we asked that then how it is in the public domain that Vietnam is having 22% of the reserves. They said that we have not done that. It is basically USGS data, and we are not sure whether that many reserves are there. So means basically reserves do not matter when we have to use the material for any product manufacturing. What matters apart from the reserves and resources? What is the quality of the reserve? What is the grade of the material? Whether it is in the adequate number which can be extracted, what kind of grain size is there, whether it can be extracted and utilized. So this is where internationally, when the reserves are defined, there is, in addition to that, it is mentioned that what is mineable reserves, and mineable reserves include the grain size, the grade, and various other parameters, which helps the miner to produce exactly what the industry needs. So this is a very famous diagram, which I think everyone would be knowing. So I'm moving forward. Now, occurrence of rare earths is through the primary source as well as the secondary source. So we are into the placer deposits area, and these placer deposits areas basically the polymetallic nodule. And apart from rare earths, variety of minerals and other elements are produced which I'll be discussing later. So why rare earths are coveted? Because it can impart host of properties which include electrical, catalytic, metallurgical, magnetic, luminescent, nuclear, optical, etc. So depending on this requirement of a specific property, then this particular element to a required quantity, required form, required percentage, it is added either in the chemical compounded form or in the alloy form to provide these properties. So here I would like to make a mention of another specific aspect. See, when now we have experienced with while working with my BRC colleagues, when we extract metal from the oxide, a lot of process is required there, which they have developed. Then these are all energy intensive, manpower is there, machinery is utilized. But international price, when we see that the metal extracted from the oxide and the oxide is almost placed at the same level. And beyond that, when it goes to the alloy level, the alloy prices are even lower and magnet is somewhere nearby. So now when this was the situation, some of the countries went to WTO and they have alleged that China is using a means unfair practices by keeping this kind of prices. But still China won that case. The reason was this, it was very simple and very very clear in the sense that when it is a metal, it is not very useful and therefore not much demand is there because there are very few users. When it is alloy, again the same thing. But when this alloy goes into the product in the form of magnet or any other form, it is providing multifold improvement in the properties of the product, and therefore the product prices increase multifold. So whatever we are losing here, that has to be recovered at that level. And on that ground, China could sustain their case and there was nothing adverse with them in the WTO. So these are again, what are the important rare earths? So this neodymium, dysprosium, europium, terbium, and yttrium. And out of them, in our resources, mostly neodymium is available, but other elements are either at the ppm level, like dysprosium is at the level of 1 ppm, terbium is at the level of 0.5 ppm. But we are extracting dysprosium and we are also in the process of developing process for extraction of terbium. So this is the chart. Apart from rare earth, the other critical material which are used for various other applications. This is again in the clean technology. What are the areas where this rare earth material can be used? And I think audience is very familiar about it. For the sake of students, if we move from onshore to offshore for wind energy generation, then this consumption of rare earth increases. Same way, if we move from a sedan car to electric vehicles, again the consumption of rare earth increases. Then when we move from a normal fighter plane to F-35, consumption of rare earth improves multifold. For example, dysprosium alone is used in F-35 to the extent of 437 kgs in each fighter plane. And this is the area where normally what we see in print media, the trade war between China and US. So it is basically for this kind of element. It is not for the normal rare earths like cerium, lanthanum, or even neodymium. So it is mostly for the heavy rare earths. Same way, for getting the bright colors, various rare earths are finding their applications. Now, this is because there are variety of applications of rare earths. So we have tried to arrange it in a form so that it can be seen at a glance. So there are defense, nuclear, metallurgical, phosphorus, medical, catalyst, space, glass, magnets. So these are different applications, and what are the materials used is also shown here. Here, I would like to share one of our experience that initial days, IRL was producing mixed rare earth chloride, and that was supplied to various users globally. So by 1978 or 79, we could earn a big global customer, that is WR Grace, who were making the catalyst for the oil refineries. And they were buying this mixed rare earth chloride from us. So in that, there was cerium, lanthanum, neodymium, all elements used to be there. But suddenly by 86 or 87, we find that the usage of purchase of our product has reduced. The reason was that by that time, they have extracted lanthanum from that, developed lanthanum-based catalyst, and lanthanum is a much cheaper material. So usage of mixed rare earth chloride is reduced. The lanthanum-based catalyst has increased. So this is the area basically we lags behind, and that is where we could not compete with China today. Otherwise, initially we were ahead of them. Now I'm coming to the Indian context. It is mostly about IREL because no other rare earth producing entity is available in the country. Other than us, only there is Toyota. So they are also taking mixed rare earth concentrate from us and then producing the refined individual rare earth oxide. So at present, we have around 7 plants, including rare earth, permanent magnet, and RE theme park, and five plants includes 3 mineral processing integrated plants, 1 rare earth extraction plant at Odisha, and 1 rare earth separation as well as a refining plant at Alvai. So apart from that, we are working on 5 projects, which includes 3 integral mineral separation and mining plant, and 1 is this titanium slag joint venture with Kazakhstan, and also 1 JV which we are working with Tamil Nadu, which is already everything is finalized but yet to register at the Company Act. And mostly we are into the placer deposits where the rare earth mineral, that is monazite, is available to the extent of 0.1%. So from here we start the mining and then we move up to the extraction of refined rare earth oxide of 99%. This is in brief about IREL. We started in 1955. In our resources, the availability of rare earths is 0.056 to 0.058%. Some of the element like dysprosium and gadolinium are available at the level of 1 ppm and 7 ppm. But today we are extracting that, and we got good support from BARC for these processes. Mostly, in general, the extraction process of any of the rare earth element consists of mining of ore and then crushing, grinding, and then classification. So here there is slight difference that when it is coming from the rock source, then this crushing and grinding is required. But in case of placer deposits, basically liberation of mineral is taking place due to the weathering action. But then thereafter, with the stream of water, it flows into the sea. A lot of churning action taking place. Along with churning, there is formation of coating, and then mixing of various other minerals will take place. So then when it comes into the placer deposit form, instead of crushing and grinding, one has to perform intensive activity of separation with the help of various techniques. Then after the separation, then classification of the grain size, separation of the grain sizes, and then if there is a coating, then removal of coating so that it can be utilized for the intended purpose. So for physical beneficiation, the methods used are gravity concentration, magnetic concentration, rotation, electrostatic separation, and then comes the hydrometallurgy, includes precipitation and solvent extraction, and finally refining of the individual RE element. Now here it shows the complete chart of aerial activities starting from the ore deposit, which we get the exploration report from AMD, mostly at G3 or G2 level. And then we have established the mining capacity of around 10 million tons as of today, operating in 8 mines in these 3 states, Odisha, Tamil Nadu, and Kerala. And then we have in the mineral segments, pre-concentration and mineral processing plant of capacity of about 600,000 ton. Very recently, we have increased up to 900,000 ton. These are integrated plants with the mines. The rare earth extraction plant or erstwhile monazite processing plant has the capacity of 11,200 tons of rare earth concentrate. And then Indian capacity is of 5,000 ton of total rare earth oxide. Out of that, the aerial capacity is around 2,000 tons per annum, and rest is the TREI, who is getting material from aerial. Now, here is the comparison of the resources. The Chinese resource grade is 6%. Our resources grade is 0.06%. So their grade is 100 times higher than Indian grade. And as a result, that the process, their process consists of just 3 stages from mining, RE extraction, and refining, whereas Indian process has to pass through 6 stages and 6 different circuits or plants have to pass through, which involves mining, concentration, processing, upgradation, extraction, and refining. So thereby the cost increases. But in case of Indian resource, because it is a polymetallic nodule, theirs also is polymetallic. So we are able to meet the cost of this processing. Suppose this would have been a standalone, then the processing cost would have been outbeaten the price which one can get from the market. Here are the various mining techniques. So this is in the intertidal zone, that is near the beaches, only manual mining is permitted. So these are the methods of manual mining. And we are utilizing the fishermen for this purpose because fishermen goes for fishing operation in the morning. So they pass through the beach. At that time, we have formed the clusters and community of fishermen. So they scratch the surface and that way the material is collected in the form of heap, which we pick up and bring to our plant. Same thing they do while returning from the fishing operation in the evening. So this is a good source of material, but this is the area where the inputs are reducing over the period of time. Then another method is the this is of dredge, which is means floated in the water pond, and then a cutter is moving downward to cut the sand, and then this is called wet mining method, and then there is a dry mining method by the excavation, and at the end a green belt is created. So this is a mining operation. Our operation is eco-friendly, unlike other bulk mineral like coal, iron, or bauxite. So mostly the bulk mining operation takes place with the help of dredge. In the dredge, this HM content, which may vary from 6 to 15%, rest of the material is quartz or silica. So after mining through dredge, it is being sent to the pre-concentration plant where the silica sand is removed and HM content is removed and sent to the plant. So this silica sand is flowed back to the mining area. So then and there, the topography of the land is maintained, and thereby by mining of IREL or placer deposit mining, no disturbance takes place to the land condition. And this is the different stages of creation of the green belt. Here you can see that this is again a dredge operation. And if the mining resources are up to a greater depth, then the dredge has to go much down, and then this can cut the mineral, and these minerals can be processed in the dredging through the dredging operation. So the various stages of operations are shown in the successive slide. So this is the mining operation where when we look at the rare earth oxide, this is at the level of 0.06% and that is embedded in the monazite. So actually what we are doing, we are mining the BSM ore, which is actually a mineral sand. And in India, it is called BSM ore because it was found with the beaches. So at that stage, there is 0.06% rare earth. The next stage with the pre-concentration, when the THM improves from 10% to 90% roughly, then the rare earth improves 10 times by 0.6% by passing through the set of spirals. There are 3 types of spirals. And after that, in the third circuit, the REO is improved up to 25%, where this concentrate is provided as an input to the mineral processing plant, and these mineral processing plant, with the help of conducting, magnetic, and specific gravity methods, separate this into form of 7 minerals. So in that monazite, which is there as a RE-bearing mineral, that is forming as a tail, or in the tail there will be monazite available up to 15 to 35%. That is further upgraded up to 96%, and then it is taken for the chemical cracking in monazite processing plant, which we call at rare earth extraction plant today. And here first the phosphatic impurity is removed, then mixed RE concentrates are extracted, and at that stage thorium and uranium is also extracted from this process, which is concentrated, and then thorium is stockpiled and uranium is supplied to BARC. So mixed rare earth, which is produced from the rare extraction plant, is then taken to a refining unit where solvent extraction is used, and this process is separating first the stream of heavy rare earths and then high purity lanthanum, NdPr, and cerium is produced, and then it is refined up to 99.99%. In the middling, we get the samarium gadolinium, and then after purification, now we are also producing samarium gadolinium, etc. So this is the collective effort of DAE in the form of BARC and DAE. Then this magnet plant was last year inaugurated by Honorable Prime Minister. Then in our Bhopal plant, we have, in fact, the group of Dr. Tiwari has worked on this for development of process, and they are also supporting us for hand holding. Dr. Sahu is visiting frequently to Bhopal plant. So this is a simple schematic diagram that how lanthanum metal and cerium metal is prepared. So this is preparation of chloride in a chemical reactor, and then preparation of electrolyte, then molten salt electrolysis, and then recovery of chlorine gas, as well the electrolyte recovered for the reuse. So in this, we have followed a method. First, we have requested BRC to develop the process at the lab scale. They have successfully developed. We have entered into understanding that this technology will be provided to IREL. And then IREL has done the basic engineering, detailed engineering to set up the plant, to create the automation level and scale up to an extent so that the engineering aspects can be settled. So there is a good hand holding from BARC. So we started, when we started the production, I think very quickly we could reach to the purity level as was the desired. So now lithium and cerium metal process is developed, plant is established, it is producing. RE recycling is also established, and this is in the process of stabilizing. Next is our target is ND metal, which is through calciothermic process, and this will be set up by September. The basic engineering and detailed engineering is already developed, and the placement of order is also done. Now we are expecting the equipment shortly. And in all these processes, there are certain equipment which we don't get because of being an entity list, but somehow we could find some solution. So means these equipments are available with us now. This is a picture of that Bhopal plant, and I invite all of you, whenever you get opportunity, please visit this plant. This is something which is 100% self-reliant activity, and I would say that because I have been part of various committees where this indigenization is the prime objective. So if I look at to these processes, these are much more ahead of those things because this is almost totally the indigenous effort. Then apart from that, this is heavy rare earths extraction process which we have developed. Then we have also developed thermal barrier coating, and this Ethereum-based catalyst was developed. But the field trial is on with Mahindra and Varroc. If it comes, then this catalyst import can also be reduced. The thermal barrier coating is successfully coated over Sukhoi 30 engine and performed successfully as well with IG car when Dr. Modali was there at the time. This experiment was done successfully. So global RE ecosystem, when we say, you can see here mining is taking place in various countries, but extraction, refining, and there afterwards, very few countries are there. India is available there because of efforts of DAE. But when we look at the mining, many of the countries where mining is happening, this all ore goes to China. Such countries are Brazil, Madagascar, Myanmar. So all these, even USA, the ore is going to China. So therefore, processing plants are not there. Then there are many challenges in rare earths. So because we have overcome some of them, as far as process and technology is concerned, we have overcome the separation of radioactivity and then concentrating it to and utilize it for the DAE purpose. But there are certain questions like too long gestation period. We are yet to find a solution for it. Then rare earth ecosystem is very long when it comes in the form of product. The country has to find solution for this. We are supporting various policy making bodies and hoping that in the days it would be achievable. And then another important thing is that this rare earth has various resources globally, and nowhere the same process can be deployed. Like for example, when we went to Vietnam or when we went to Oman, we found that the resource available there we may not be able to use our current process. We may have to develop a new process. Same way, the resource which was found in Ambadongar, Gujarat, in order to make usable to our current process, I think again 3-4 steps or 3-4 plants have to be established, which we did technical feasibility way back in 2021. So we have a good potential of rare earths because we have the capacity, we have the capabilities, we have a world-class laboratory for undertaking any kind of developmental work. So only thing that if the usage can be developed in the country, products can be developed where these ingredients in the terms of rare earths can find place, then probably we could be a part of developed economy very quickly. Thank you.
The talk is now open for discussion and questions, if any. Perhaps you can come on the mic.
Year, Government of India allowed few private companies to mine rare earths in India. What will be its ramifications to?
See, rare earth field or mining of rare earth has never been blocked or regulated. It is open right since 1947. So when the source is monazite, because it has the radioactive element, thorium and uranium, therefore it comes within the purview of DAE. But if it is through some source where radioactive elements are not there, it can remain open. Same way for import and export, also rare earth is open. But I'm surprised to hear that last year 4-5 people have been allowed to mine. As per my knowledge, nobody has been allowed yet. So-
Actually, was allowed that we can mine some of the rare earth along with some of the transition elements which were not.
No, yeah. So again, that resources are free from radioactivity. So then last year, actually, that paper first came to DIE. Those resources are in Karnataka, somewhere Chhattisgarh. But those auctions are not successful because the process for extraction has to establish first for quoting the rate in the auction. So then the paper which has come from Ministry of Mines was related with the fixing of royalty. But those mines are yet to be auctioned.
One more question. In the develop rare earth free lightning materials or rare earth free phosphorus.
I think that answer from BRC will come.
Manoj, a lot of work is going on, including in RCIG, your division.
From impetus from the government.
No. First, let technology mature. So far, it is done. A lot of work is being done on rare earth-free light emitting sources. Defect-induced emission, for example, is one application. But believe me, they are yet to graduate from publication to next stage. So GOI's role comes much later. Yes. Alnico permanent magnets are rare earth-free, but they are not as good as neodymium iron or samarium cobalt. Alnicos are known for last 25 years.
Lithium minerals in Jammu Kashmir.
No. China may anytime may take advantage. So it may lead to disruption of supply chain and also it lead to economy of.
This is a very good question. I will tell the genesis of this question. See, what happened that when China developed the process of rare earths, before that, US has developed it, and they had the best mine of the world, 8.9% grade, and they were producing europium. They were producing all the rare earths. Then what happened? They found that China is also having this process, and their environmental laws were becoming stricter because this by 97 in Kyoto Protocol, they have been capped for I think 6 or 7% of the emission. So they found it easier to offload all their rare earth processing to China. So ore was the US, it was going to China. After processing, it was coming back to US. This is the real situation. Then after some time, many people started writing in the print media of US that it is our resource, low value ore is going to China, then refined material is coming here, so it has to be stopped, we should develop there. This is not the situation in India, but some people have copied, and in our print media and electronic media, this news started coming. See, we are only handling rare earths. Nothing goes from here to China, and hardly anything comes from China here. What is coming is dysprosium, terbium, which are heavy rare earths. But what quantity it is coming? It is being used in the laboratory. We don't have industry who can use the rare earths. So what is coming from China? Where are we dependent on China? See, today we are struggling that our industry, our system to start utilizing available rare earths, because all rare earths are there in our warehouses. There is hardly any industry who takes it. So then what will come from China? So it is only a imported media news. What is coming is in the form of alloy. In India, what is produced is oxide. Oxide to alloy is a, in addition To that, there are two plants requirement, specific technology requirements. If we develop that, obviously this rare earth will utilize and we will not depend on China or any other country.
But India is having abundantly rare earth materials, but
Look, without technology, how we are extracting it? We are producing at means industry level, tonnage. I have just shown.
it is not up to the mark.
What way you are saying up to the mark? Then how? You tell me that Toyota.
Compared to other countries.
No, this is perception because our perception is that we are poor. But do you know that the best electric vehicles who produce Toyota? They prefer Indian material, not the Chinese material. Are you aware of this? They have a plant adjacent to our plant. They use our material, and when utilizing Indian material, NDFEB magnet was made, its performance was better. My BRC colleagues knows that. So please remove this perception. We are not depending on anybody. And as far as increasing the production is concerned, when the resources are granted, there is no dearth of capacity and capability. We can very well achieve those numbers, but we cannot change the nature. If their nature gives 100 times more bigger grade than us, then obviously their volume will be higher. If they have the liberty to go anywhere and mine from there, which we do not have, obviously their numbers will be more. But capacity and capability, we are not any lesser than them.
The international prices of the rare earths produced by China and India, are they comparable?
See, I think this answer I included in my presentation. International prices, on one way we can say that they are manipulating. But if you look at, this is a market material. It is not a regulated material. It is not a means material which is preserved. So then what is followed is demand supply economics. So when we look at the rare earth metal, how many people need that metal? Only few industries who are capable of converting. So demand is less. Therefore, the prices are not much. Again, in form of magnet, demand is not much because there are substitute magnets. But when this same magnet in the form of BLDC motor goes to some kind of industrial automation or industrial gadget, that gadget value is very high because it gives energy efficiency. So all price you are recovering there. So if you look at the market risk, market economics, market governance, then those prices also one can justify, which China did it in WTO, and that's how they could survive.
First you ask. Next.
Yeah.
So the skies and blah blah.
Pyrocore also.
Single. So it was a story that didn't go further. So 16 and that was nothing about
Interview.
So I'd like to know for the time.
Yeah. You see, today, I think the sustainable development is the very major requirement. So, world over, anywhere we attend the conference, I think the focus is that area. So, this process which we are working today with minor modifications here and there, actually, it's a old process. This basically purchased from the French in 1950. So, I feel that there is a lot of scope for the development, and sustainability is a major area where we can make a big thing. And second is artificial intelligence. It means embedding that artificial intelligence into this process. So that way means wastage control will also happen, recoveries would improve. And third thing, if when materials side we come, what I have found that, and we have always, I think AMD is also maybe there on that. We always have a difference of opinion with AMD because their geological report says some number and our report of extraction shows some different number. The difference is because grain size differs. See, more than 300 micron is not usable in the industry. So we will consider up to 300 micron. But from the geological report, it will consider of any number of micron. So rest of the material we keep as a subgrade material in our mines area. So in the days to come, we have to develop the technology which can utilize this lower grain size of the material. And that is how the mining industry works year after year. So these three areas are still very much open.
It is
I have one question, but before that, I must apologize that it seems I promised a talk and I could not do. And I tell Director Materials Group that now I will do. I have a full-fledged talk on science of rare earth. Technology, I think you people know much better than me and other. But science of rare earth, I'll be very glad to come to Board Lab and deliver a lecture. I request Director Materials Group to please coordinate. Sir, I have one chemistry type question. Since I'm a chemist,
I don't know whether I'll be able to.
we will discuss separately also.
Yeah.
Out of curiosity, see, wide variety of uranium ore grade is well understood because in geochemistry, we know in earth abundance, wherever we had oxidizing compounds nearby, U4 gets oxidized to U6 and U6 is mobile. So it goes to seawater. That's why India has got maximum 0.04, 0.05% of uranium compared to other countries like South Africa and Brazil, etc. In case of rare earth, we know it is predominantly 3+, nothing can be oxidized, and only one or two can be reduced, europium and lutetium, europium and ytterbium. So what leads to 0.06% to 8.9% abundance?
Yeah, actually,
The geochemistry, out of my curiosity.
basically, this is the difference of the resources. Like here in placer deposit or in our resources, it is embedded in the monazite. So extraction of rare earth is not exactly a mining process. It is beyond mining, a chemical process by which the extraction takes place. And then in the process, there's so many other element also comes. Yeah. But where 8.9% is a carbonatite resource, so they are all primary resources. So that's the difference. So there, this carbonatite resources will come based on the deposits which we have studied with iron, like US or iron, copper, and gold in case of China.
They are
So-
carbonate type.
Carbonatite.
Yeah.
Yeah.
And recently in India, we also have found some xenotime.
that is carbonatite Ambadongar deposit we found.
It's a good sign.
But that grade is 1.5%. One slide I didn't have, when we compared across the globe, up to what extent carbonatite deposits will work out economically viable condition. So we have found that the last number is 5.5. Below that, no deposit is operational across the globe. Say even Brazil has 5.2%. That's not operational. Then ours is 1.5, and we did a technical feasibility study for 3% ore of Ambadongar. So even there also, unless otherwise the other element we extract, it was not working.
Economical.
Yeah, yes.
Thank you very much.
Yeah, actually, sir, I will just add, it's a theoretical answer, which I read on something. See, what I understand is that when the earth was solidifying, the most of the mineral which have the highest melting point, they gone on the center of the earth, or the close to the mantle side. Rare earths were the one of those elements which have first solidified, one of the first which were solidified. And in India, or in world rather, wherever earth crust is moving up, the geography of the earth is pushing the rock up. Those are the lucky people who get rare earths. China is one of them. Brazil is another one of them. In India, this ore came because of the seabed. So what happens? These rocks are pulled up by the wave with a very high velocity. But when the wave goes back, the energy is lost. So it gently takes off. So millions of years of this movement has taken that light element out and only heavy element left. So we are getting the trace of what was left in the past. That is the reason.
This looks very convincing. At the same time, I'm happy that, I am in touch with AMDR also in various ways. So what they say that if you do uranium mining much deeper, the quality is going to improve.
Yes, sir. Actually, in Tumlapalli, the deeper mining is showing much higher concentration of ore. Problem, many times I also talk to them in MD, and sometimes I don't want to go in the heated type of argument. I am telling that Himalayan is the region where we are likely to get much richer rare earth as what you're finding in the seashore. But nobody wants to go to the height of mountain because of the obvious reasons. So their entire geographical survey is on the near Himalaya,
Yeah.
but not in the center of Himalaya.
The same could be true for REs also. Once we go deeper,
Yeah.
from 0.06, we may go to 1% or maybe whatever
Yes, sir.
number, anybody's guess.
That's why I'm saying the KPK region, which is in POK.
These are the region that is why China wants to come this side. They want to occupy all those regions where earth is moving up. Rather, they are not interested in Bhutan, they are interested in Nepal.
Nepal and Afghanistan also.
Yeah.
Same reason, mate.
Thank you so much, Dr. Singh.
Online participants,
There was a message.
any message, any question?
Are there any questions from the online participants? If yes, you can kindly put them in the chat box.
Yeah, I saw that.
Yes, there are no more questions. I would like to thank Sir for a very in-depth, insightful and lucid talk. The importance of rare earths is indeed visible in their diverse applications, especially in the sector of clean energy. So with these words, as a token of our appreciation and heartfelt thanks to Dr. Singh, I would request Honorable Vice Chancellor to present to him a souvenir. Towards the end of the program, May I now request Professor P.C. Selvin, Registrar HPNI, to propose the vote of thanks.
A very good evening to all present here and who have joined us through online for the third Dr. Srikumar Banerjee's memorial program today. I submit our heartfelt gratitude and thanks to our chief guest, Dr. Deependra Singh, Chairman and Managing Director, Indian Rare Earths Limited, for accepting our invitation and delivering the lecture entitled Rare Earth Discovery, Development and Deliverables. He has touched very many topics, starting from the critical materials, 3D approach, and he has beautifully explained the zero waste technology, what is the need of our towards the sustainable development of any country. And he has proved that our DA's approach is really an indigenous development of all these things. And our rare earth materials are invited by international community like Toyota, and there is no necessity for us to have any inferiority complex over our technology. Thank you very much, sir. The rare earth elements perplex us in our researches, baffles us in our speculations, and haunt us in our very dreams. The strength they stretch like an unknown sea before us, mocking, mystifying, and murmuring strange revelations and possibilities. This is a statement made by William Crookes in the year 1875, whose functional discovery, Crookes tube, changed the whole chemistry and physics. And still, this statement stands true and gives us a lot of opportunities. Thank you, Dr. Singh, for making such a wonderful speech today. I thank Dr. A.K. Anand, former Director, Reactor Group, BRC, for joining us today, who is a close friend of Dr. Banerjee. I thank Professor A.K. Tyagi, Dean HPNI, for proposing the formal welcome address for the program. I thank our Honorable Vice Chancellor, Professor Yukamachi Mudali, for his presidential and introducing the chief guest. I thank Dr. Rachna Agrawal, the program coordinator, for all the necessary arrangements and meticulously planning the events with utmost care. Thank you, ma'am, for your MC also. Thank all our associate deans and assistant dean in our officials for joining the event. I thank all our directors, deans, academic and dean student affairs, conveners, board of studies in the CIS OCC for joining the program through online. I thank all our scientific officers from BRC, faculty members from HBNI, and students of HBNI for your on-site and online participation in this memorial program. I thank our IT technocrats of HBNI for the audio and video arrangements. I thank you one and all. Jai Hind.
So much, sir. Heartfelt thanks to Team HPNI as well as all the participants for making this program successful. Your presence and support is truly appreciated. With this, we conclude this program. Please join us for refreshments outside. Thank you.